Morning, guys. This will be our second lesson. Because it's been our break, I just wanted to go over with you the second main chapter that we did. Tomorrow we will be starting into new stuff with momentum, but for the time being, you can look over the key ideas sheet again. I'll attach a soft copy under the handout section if you need to scribble over it. We had already used this before we prepped for the forces test, but this would be a nice summary of some of the main ideas from dynamics. So here we go. So this is chapter 2 on dynamics. The main concept with dynamics was the notion of a force. We're going to use F for it. Because forces are vectors, usually you're going to see F with an arrow above it. Forces have direction, because if you imagine when you do pushes or pulls, you can push or pull in multiple different directions. Remember, for a vector, the size of the arrow indicates how large it is, whereas the direction is given by the arrowhead by itself. So this whole chapter has been looking at different types of forces. It's been fairly systematic. We try to just step our way through formula by formula. The first formulas that we deal with is this notion between mass and weight. If you remember mass, just hint for yourself, mass has to be measured in kilograms. That's a nice reminder when we actually do physics problems. Make sure anytime we're given something in grams, we actually convert things to kilograms. 1,000 grams is a kilogram. Mass actually describes the amount of matter, the amount of substance that's made out of the atoms themselves. So whether you are on the Earth or whether you teleport to the moon, as long as you don't lose an arm along the way, your mass won't change. When we use weight in science, however, weight is another name for the actual force that the planet pulls down on you. So weight, typically you can say W or you can just say Fg, the force due to gravity. This one here, we always have a formula for it. On your formula sheet, Fg is equal to mg. And for us on the planet Earth, G, near the surface of the planet, we've been using 9.8. We started seeing problems later on where the directions were a little more challenging, so we don't necessarily want to just use positive and negatives. We found that by doing what's called a free body diagram, I can actually indicate to you which direction the forces are pointing to figure out whether things should be positive or negative, and that avoids the hassle of, even in the math, for us to have positives or negatives. So this one here is the weight. This is always going to be your starting point, just simply mass times gravity. As a second force here, we dealt with a guy called the normal force. It's normal in the sense, normal means perpendicular, so 90 degrees. So as long as, let's say I'm on a flat surface here, let's say I'm just standing here on a flat surface, because my surface is horizontal, the normal force is going to be perpendicular to the surface. I sort of know the answer here. When I'm standing here, I don't either sink into the ground nor the ground pushes up on me. We know then, because gravity is pulling down you and the ground is supporting you, both of them end up canceling out for us to stay stationary, for the acceleration to end up being 0. The little bit annoying thing with the normal force is there's no formula for it. It really depends on your picture. Sometimes the normal force is bigger or smaller depending on the situation. You're not going to have a formula sheet for that part. For example, we did the analogy of, let's say there's a bird that comes up behind you, grabs you from your shoulders, and then applies a force going upwards. It is totally possible that the bird can actually pull hard enough to lift you off the ground. In that case, their Fa would have to be bigger than Fg. But more so, what I'm picturing is the bird is trying to support your weight, but it's not enough to actually go against gravity completely. What's going to happen here is when you start looking at the tug of wars, you deal with your teams. Well, because the bird is supporting you, but you're not going any up or down, the net force is still 0. The teams are, gravity is still trying to pull you downwards against Fa again and Fn, against the applied force on the bird multiplied by the normal force. So in this case here, would the normal force be bigger or smaller than gravity? In this case here, if you said smaller, you're correct. The normal force is sometimes referred to as your apparent weight. So because the bird is supporting you and is lifting part of your weight, you're going to end up feeling a little bit more weightless. So you're going to end up feeling a little bit lighter, and that sort of tracks. The ground also needs to support you a little bit less. So we've dealt with force of gravity. You always have formula mg. Depending on the situation, you can find your normal force. The reason why we want to find normal force is our third formula, which is friction force, depends on the normal force. For a friction force, no matter how smooth surfaces feel macroscopically, there's always intrinsic grooves on one surface. There's always grooves on the other surface. Depending on how interlocked these grooves are, they may not necessarily be perfectly fully into each other, but depending on how much they are, as I try to pull this object, let's say I apply a force to the right side, I'm going to need to overcome, I'm going to need to pull hard enough that these grooves can actually come out from each other. We did a lab on this one here that there's two different types of friction. If your object is currently at rest and it's actually not moving, and I pull it to the right, this is referred to as overcoming the coefficient of static friction. Static means it was stationary to begin with. As the object is already sliding along though, we don't really give it any chance for the grooves to really interlock as bad as it was earlier. It's still going to apply some friction, some force against yourself, but what we're going to have here is instead a coefficient due to kinetic friction. Aside from the lab where we actually separated those two and we made some comparisons, we're going to see in our generic formula here, also on your formula sheet, FF is equal to mu Fn. We're just using one generic mu to represent both types of friction. Sometimes it's obvious when it says, oh, what's the coefficient needed to start motion? We know that means static. Sometimes it says to continue motion, we know it's kinetic, but we're just going to deal with this as just one general constant. The number never gets to be very big, but there's no units, and it describes the bigger the number, the more roughness, the more friction is between the surfaces. Remember, for this formula here, when we calculate an FF, this FF here is a maximum. This is, depending on how interlocked the grooves are, this is as much the ground can go against you. If in the situation like the bird, they're not actually pulling hard enough to actually lift against you, it's possible that I can apply an FA that doesn't actually win out FF. Let's put some numbers to it here. Let's say the maximum friction we calculate is a total of 50 newtons. There could be a maximum of 50 to stop you. If I push with only 10 newtons to the right, I'm not pushing any near as hard as friction is pulling. Because friction is known to only oppose motion, friction is a little bit lazy, just like normal force. Although friction might max out at 50 newtons, friction will then say, oh, you're only applying 10 newtons, I only need to go 10 newtons and I've already cancelled you out. Once I've cancelled you out, therefore we're not going to have any motion anymore, net force is going to be 0. It's only going to start moving if instead of pulling, let's say 10 newtons, let's say I start pulling 120 newtons as an example. Okay. In this case here, even when friction is complete maximum, which is 50, I'm pulling much harder than that. Here's our tug of war. I'm pulling at 120, 50 is going against. We have a net unbalanced force of 70 newtons, which we'll use in Newton's second law to calculate acceleration. So that's how you use that formula there. The friction force in newtons is calculated as a maximum amount of friction there is. A couple other nice general remarks based on this chapter. A lot of this dynamics and forces stuff that we talk about can be summarized by Newton's 3 laws. I'm just going to go over them one by one in turn for you here. So Newton's first law here, it says objects remain in uniform motion. Uniform motion is another way of saying constant velocity. The velocity doesn't change as long as there is no net force. Remember in this case here, sure, if an object is at rest, if an object has velocity 0, if there's no net force, it's just going to continue at velocity 0. It's just going to sit there, no problem. Let's say we were in space, however, where I have a box. Let's say this box here was already moving at 10 meters per second. In space, this object here will, in time, will keep moving along, but it's just going to continue at 10, at 10, at 10, as long as there's no net forces applied. What net force might look like here is maybe I try to push at it from the backside here. I try to push at it with, say, 5 newtons. Someone else comes along, tries to push against me at 5 newtons. Those 5s will cancel out, so that again there's no net force. Even though there are individual forces being applied, because there's no net force, there's no acceleration. Sort of the main takeaway from this here is force is not needed for motion. Okay? Motion can continue to happen, but what we'll see between Newton's first law and Newton's second law, force is needed for acceleration. Force is needed when there's going to be a change in speed, either a speed up or a slow down. Remember the net force, what we're going to talk about in Newton's second law, F net is equal to ma. We have this on a formula sheet. Net force by itself is not by itself a push or pull. Net force is the overall unbalanced force from the tug of wars that are being present. So for example, earlier, the tug of war was actually between FA and FF. I didn't actually draw an arrow to say, oh, net force one way or the other. I looked at just the tug of war and I said, well, if FA is 120 going one way, and FF maxes out at 50 going this way, when I do the tug of war, we have a net difference, an unbalanced force of 70 newtons. It's that 70 newtons which we call net force, even though by itself it is not its own pressure. If there is a net force that's being applied that's external to the system, the net force will cause some acceleration. Depending on which direction your velocity is, acceleration, if it's in the same direction, it'll speed objects up, accelerate. If it's in the opposite direction, it'll slow things down. So in that case there, net forces are needed to cause acceleration. Or better yet, if you know that things are at constant velocity, if you know that there's no acceleration, you know that the tug motors have to cancel, there is no net force. So that's Newton's first law and Newton's second law. Newton's third law is the one that's sort of best known here. Usually you say for every reaction there's an opposite reaction. Be really careful when you deal with this force here. Let's go back to this picture with FA and FF. I know FA is pulling to the right. Earlier, based on my numbers, I know friction loss, so the arrow is a little bit smaller. What Newton's third law does not say is, oh, FA against FF, one's pulling left, one's pulling right, they have to cancel. Well, no, they don't. In this case here, we said we had a net force going to the right. For Newton's third law to apply, we have to look at each force individually. So for example, if you just look at the FA by itself, I'm pulling on this object. Earlier I think I said 120 newtons. As my hand pulls on the box 120 newtons to the right, it's sort of like the box also pulls against me 120 newtons. That is not a force of friction, that's just an equal and opposite pair. In a similar way, friction, I was quoting the number, maximum friction against you is 50 newtons. But as the ground sort of scrapes against the box and provides a 50 newton force to the left, the ground is also the box is also pulling the ground along, also with a similar 50 newtons. So when we do equal and opposite, it's not always obvious. It's nice when we do tension, basically the strain will pull on both sides in equal and opposite directions. But other than that, we still need to use free-body diagrams, figure out tug of wars, figure out who wins to actually figure out acceleration. So, I'm going to give you an example. Let's say here's the Earth, and here's the Moon. We see another example of this Newton's third law played out. Usually we just think about the Moon in orbit around the Earth. The Earth is a mass, the Moon is a mass. There is going to be a force of gravity. It's always an attractive force that brings masses together. Just like the Earth pulls the Moon with some force of gravity, when we say equal and opposite, the Moon actually pulls the Earth with an equal strength, with the same force, believe it or not. That's the third law. That's equal and opposite. How come then we don't see the Earth actually revolving around the Moon? If you start thinking about, let's say, F9 equals ma, F9 equals ma, even though the forces are equal in both cases, the gravitational pull on both sides, like a string connecting two objects pulling things together, are the same, even though the newtons are the same, because the Earth has quite a lot more mass, the amount of acceleration that you notice here is fairly small. The Moon, although quite substantial in comparison to mass, is fairly low. The acceleration is going to be much, much higher. In Physics 12, we're going to come back and we're going to see it's because of this center-looking force, we're going to call it a centripetal force, that actually allows it to stay in circular motion. If I, at one point, cut off the force of gravity, the Moon would just head off in tangential velocity, it would just go off, straight off into the Earth. Remember, as we start doing these force problems, it's always a good idea to start off with a free body diagram. A free body diagram, unlike the detail where, the Earth may have different densities, may have different parts which are a little more massive, a little less massive, has certain shapes and has certain sizes to it, free body diagrams just simplify things and basically say if the whole Earth was squeezed into a singular point called the center of mass, similarly the Moon was squeezed into a center point, we can just look at how does the center point on the Earth interact with the center point on the Moon without really worrying about the actual distribution. That's what a free body diagram tells you. We mentioned earlier, because the pushes and pulls might end up in diagonals, it's a little bit harder to track in this chapter positive and negatives. The free body diagram will show you the directions for it. During our lab, we used a meter called the spring scale. Spring scales, or spring force, is demonstrated by something called Hooke's law. And Hooke's law basically says the elastic force, the amount of stretchiness in the spring, is going to be proportional based on the material. Some springs are easier to stretch, some are not as hard, but it's proportional to how much the spring is being stretched. So if we think back to that spring scale that we had from earlier, okay, before you hang a mass on top of it, the spring already had a length. Let's call that L naught. Usually when you see naught, it means something is initial. Then what we did is we came along as we added a mass. Because there is a force of gravity on this mass, it's going to end up stretching the spring out further than it wants to be. Now the spring is going to have a different length. We're going to call that L. When we're trying to find which force is proportional and whatnot, this x here, be really careful, it's just the extra distance the spring is being stretched. So in this case here, x is actually going to be the whole length the spring is right now, minus off the natural length of the spring itself. Just to remind you, the spring force is in the opposite direction. Gravity is pulling downwards, the force in the spring is trying to restore the length back upwards. Sometimes Hooke's law is written with a negative there. Again, something that's solved when we do a free body diagram. If I have a negative, I know it's in the opposite direction. Even when the picture gets to be more complicated, say a gravity on slope problem here, when we're on the slope, gravity doesn't care. Gravity just pulls objects straight down to the center of the earth. Instead of staying in a regular coordinate system, let's say x and y, this object isn't expected to go straight through this way or up or down this way. So what we did for a gravity on slope problem is we decided to twist our coordinate system a little bit. We defined a new horizontal, we'll call that x prime, going up and down the slope, and we're going to do y prime that goes perpendicular to the slope, x prime and y prime. In that case there, we're going to find the normal force, which is perpendicular, being 90 degrees from the surface, which is slanted. That's perfectly in our new vertical y prime axis. Our x direction could talk about the object sliding up or sliding down, so that's already along the slope, which is nice. The only diagonal we would need to break up into components is going to be this gravity. The gravity, which used to be straight downwards, needs to be broken up into two parts. We're going to call this an F in, sometimes called the squeeze. The squeeze is the object on the slide, and an F down, which is the force that's responsible for things sliding down the slope. We did the trigonometry in class together here. We saw that the theta that's in on the ramp itself always amounts to this theta for the triangle, which means that the F in is always going to be the cosine side. It's always going to be the adjacent side to the hypotenuse, whereas the F down is going to be the sine side. So you can memorize those formulas if not, but it should be pretty easy enough. Draw the straight down for the gravity, draw one arrow that's perpendicular, that's going to be sort of against Fn, and the remaining force will be F. It is a temptation sometimes when we do free body diagrams to include too many forces. So in this case here, if I set this object at rest, I'm expecting this object, if there's not enough friction, to slide downwards. Don't suddenly put a downwards arrow unless there's implications, oh, there's a hand and it's physically pushing it downwards. But we'll actually realize the force that's actually taking it downwards is actually the F down part of gravity. So just be careful not to put too many arrows. Only put arrows when it actually is a push. Towards the end of this chapter here, we made a connection back to our kinematic section. And this basically comes in handy when we do Newton's second law. This gives us a nice connection based on the push and pull stuff that we do with forces and connect it back to acceleration. Forces are sort of free body diagrams, we do our angles, and we figure out what's the net wind. If there is a net force and it's not zero, this will amount to some speeding up or slowing down. And once we have acceleration, we're back to using our kinematic formulas. We have these from yesterday, also on your formula sheet. Sometimes you're given questions where you know all the kinematics, you know displacement, you know the time, the speed change, or whatever. If you can somehow find an acceleration, that will also link you back to that net as well. So this formula acts nicely to connect the two chapters so far. On the back side, as we deal with one last formula, our formula so far, Fg is equal to mg, was a somewhat of a simplification. We've been using g as a 9.8. The g value here is called the gravitational field strength. It amounted to 9.8, but what it hides within it is actually a true constant in our universe, gravitational constant. That's on your data booklet. It's hiding, in our case here, the mass of the Earth, as well as when I'm standing on the Earth's surface, I'm imagining I'm a distance of a radius away from the center of the Earth. I'm imagining this is the surface distance squared. So when we deal with the 9.8, the 9.8 is actually hiding quite a lot. And basically, if I know, and if I assume all the questions we do, pulley questions, spring questions, all those questions are on the Earth, we're close to the Earth's surface, I can pretty easily just end up using that thing. This formula here, Newton's law of universal gravitation, is on the formula sheet, especially important when we start dealing with planetary sized masses. You just need to remember the G here, which is called the gravitational field strength. It's sort of, out of this formula, it sort of pretends you're not there, it erases you. Imagine that the M2 is not there. The gravitational field strength will be the amount of gravity a test mass would actually feel if you were some distance from there. So if you suddenly come along and say, oh, I actually have 50 kilograms, I can just go 50 times that weight. If another person comes along, oh, I'm actually 100 kilograms, 100 times that weight. I can just use the math innate, the gravitational field strength, to hide a bunch of this detail, and it's given by this formula, not separated on the formula sheet for you, but just notice the gm over r squared without that last thing. Gravitational field, because it's inversely proportional to the radius, as we get further away from the center of the Earth, we're going to realize this gravitational field gets weaker and weaker. So the amount of pull towards center mass gets weaker. Again, I would need to know the true mass of the object before I can actually calculate the force of gravity. This part here, the formula itself wasn't very challenging, but it's just a matter of making sure you know how to type exponents. Make use of the EXP button on your calculator. It puts brackets in the right place as well. So just type things in for yourself, practice a few questions. Other than that, I could just ask you to compare by ratio. Say, for example, Fg1 is our formula gm1 m2 over r squared. Let's say the mass m1 suddenly becomes 3 times m1. It's 3 times as big, but everything else is left the same. Without actually going through the actual numbers, I can just ask you generally, well, how does the gravity in the new case compare to the original case? And all that amounts to here is when you look at your formula gm1 over r squared, the only thing we've changed is m1 has now become 3 times what the initial mass has been. The 3 can be pulled out in front. We now have 3 times what our original gravity is. Whatever the force of gravity was before, it's now been tripled. So sometimes multiple choice questions will just ask you to do things by ratio. Last thing I want to do with you in this lesson here is just to work through a few examples. So this would be a good time to have all your notebooks and you can actually try it out for yourself. It's a good idea to just press pause, give yourself a chance to actually try it out. Say we have a tabletop pulley question. I have 5 kilogram hanging over a tabletop pulley with a 2 kilogram. At first we would say there's no chance the 2 kilogram would actually pull it downwards, but we saw that in our notes. The force of gravity here actually isn't fighting against the force of gravity on the 5 kilogram. We're actually fighting against whatever friction it might be. So let me give you a friction coefficient. Friction coefficient mu is equal to 0.30. I want you to try 2 things. Find the system's acceleration. Find out how quickly both of the masses travel together. They are connected by the string, so they have to do the same thing, either fall off together or stay together. And B, I want you to calculate the tension. Anytime there's a string, there's a little bit of tautness that's connecting the two here. I want you to find the tension. So if you can pause it here, try it for yourself. Assuming you've done that here, I'm going to walk you through the problem here. So we have Fg1. Force of gravity, we always have a formula m times g. So we're going to go 5 times 9.8. So this one here is 49. In a similar way here, Fg2, if I go 2 times 9.8, that gives me here 19.6. We have a tension force, that's going to cancel out, it's equal and opposite. So I can't deal with that right now when I'm looking at the whole system. My free body diagram would also say there's a normal force from the table, because again I know this object neither falls through the table or bounces off the table. I know the Fn is actually going to be 49. Given the mu, we can calculate a maximum friction. Ff is mu Fn. Mu is 0.30. The normal force happens to be 49 this time. 0.3 times 49 gives me 14.7. And now when we look at our tug of war, we have a 19.6 that's trying to pull things to the right, clockwise. And we have 14.7 maximum friction to try to stop it. Who wins between these two? This case here is Fg2. We can then set up the final formula here. F net, in this case here, we go bigger minus smaller just to avoid positive and negative kind of issues. So I know Fg2 wins this time. So Fg2, 19.6 minus off 14.7. So to give me a net force here, double check my numbers as I go through here, I'm getting 4.9 newtons. This is an overall unbalanced force. This is what we call a net force. And here's where we can use Newton's second law. Newton's second law, if there is a net external force, this amounts to an acceleration. We have a 4.9 Newton force that's pulling both masses that are connected. So 5 plus 2, you could put 7 there, and you can calculate the acceleration. 4.9 divided by 7 is an acceleration of 0.70. And a little bit sloppy with sig figs, but it's okay. Your final answer needs to just be 2 or 3 sig figs, and it should get the answer. To then calculate the acceleration, what's really nice about Newton's second law is so far we've done F net equals ma for the entire system all at once. The tensions that canceled out, there was no way of finding tension. Now what you're going to do is you're going to zoom in to either mass individually. I find the mass that's hanging off here a little bit easier because there's only 2 that are pushing the poles. In this case here I have 4 arrows, I don't necessarily want to deal with that, so I'm just going to go look at the hanging mass for now. Double check my numbers. I have a 2 kilogram mass. I had a FG2, I believe it was 19.6 newtons. For FG, this hanging mass here, there was tension force, maybe tension 2. And I knew for this mass here that was hanging off, there was actually an acceleration of 0.70. This is just a quick photo of how the setup is right now. When I run the clock, the system here does accelerate. With the 0.70, both masses have to have the same acceleration or the strings will snap. So I'm going to do F net equals ma again, bigger minus smaller. So 19.6, which is the gravity on the hanging mass, minus the tautness of the string T2 is equal to 2 kilograms times 5.70. That gives you here tension. 19.6 minus 2 times 0.7 gives you 18.2. This is going to be the same tension that's applied on the other side, and you'll notice, even though, yes, it is the gravity force, Fg2, that's actually, see that, but 19.6, that's actually providing the 18.2, you'll notice these two aren't equal because there is an equal acceleration in the system. Again, when you run the clock, the system pushes off. Another question I want to practice with you here is a lawnmower style question. So let's imagine we have a 12 kilogram lawnmower. I'm going to be pushing down an angle of 20 newtons. Let's say I'm pushing at 30 degrees. When I push downwards, I have an Fy down, and I have an Fx that's pushing horizontally. We're going to have a gravitational force, so Fg. Always start off with a free body diagram if you can. In this case here, I'm going to be asking you for the coefficient of friction. What is the mean? How interlocked are the grooves? In this case, what I'm going to tell you is if the object is moving at constant velocity, and you find the coefficient of friction. Again, you can pause at this point here, see how you do. As we try this out here, we're going to work with this language here. When we have constant velocity, it doesn't necessarily mean this. This one here is obviously it is sliding along, it is moving forward. But as long as your speed doesn't change, we know right away the acceleration is zero. And like we said earlier, if you have no acceleration, F net is supposed to equal to ma. If you have no acceleration, that automatically means all the forces when you do the tug of wars, all the way constant. So let's just go through this in detail here. Fg is supposed to be mg, so 12 times 9.8. 12 times 9.8 is meaning 117.6. Normally the Fg would be exactly counterbalanced with the Fn. In this case, you'll notice because my angle here I'm actually pushing downwards as well, the Fn not only needs to support gravity, also needs to support the Fy part of my applied force. So we'll do these on the side here. Fy is 20 sine of 30. 20 sine 30 gives me 10. And then Fx, which is the cosine, the adjacent side, 20 cos of 30. This one is 7. So back to this one here, we had an object that Fg is pulling 117 downwards. 117.6 downwards. We have a normal force that pushes only what it needs to, but with the extra 10 that I'm pushing downwards, the Fn would actually need to be 10 plus 117.6. Again, you're not going to get this formula anywhere. The Fn in this case has to balance off the Fa downwards and gravity. We just sort of do teams here. This is upwards and this is downwards. And if you add those up there, we get 27.6. The reason why we got normal force is because then we can go Fx is equal to mu Fn. Normally I would know the coefficient, I can use this to find the max friction. This time I'm actually asking for mu, so that's going to still be a variable. We're going to have 127.6. This means then I need another way of finding friction. If we sort of get stuck going forwards, we try to find Fg, Fn, Ff, it's good to work backwards as well. Because we know it's constant velocity, we know that the net force is actually cancelled out and we know that it's actually zero. The only forces that haven't cancelled out so far, the Fn has balanced Fy and Fg. The only force, if you look carefully, is just this Fx and just an Ff that opposes motion. Normally, this was earlier, we would say, am I pushing hard enough to move it along? Is there an acceleration? We had already decided acceleration is zero. So we know the relationship between the Fx, which is 17.3, and friction, is in this case the F net, because it being zero, actually says Ff has to be numerically 17. And with that, you can actually find mu. Again, this number doesn't get to be all that large. And 17.3 divided by 127.6 gives me a coefficient of 0. Last question I'm just going to leave for you to try out here is a gravity on slope problem. So make sure I give you all the numbers that you need. Let's say this is an 8 kilogram object. This object here is already having an inertial velocity of 5. So somewhere down here, someone had been pushing it, but at this point when the picture was taken, there is no more hand that's pushing it. It was already just given some upwards velocity. We know with the upward velocity, it eventually will end up coming to a stop. What I want to know here is by the time it hits the top, at the top we know that the v is equal to 0. I want to know how much ground, how far up the ramp does this travel before it comes to a stop. The other numbers that we will need here is, let's say we have a 60-degree ramp. If the problem does not specify friction, like in this case here, you can pretend that there's no friction, start off with a free body diagram. Assuming that there's no friction, I want you to calculate what is the displacement going upwards. Be really careful when you end up finding the net force. The net force should be F down. Because the acceleration is actually in the downwards direction, you will need to put a negative for acceleration if positive next time. So this one here would have to be negative, just for something you can be careful of. See how you do with that, and if you have any questions, just let me know.